Hello and welcome to another Tsoding session. How about that? How about that? But you didn't expect that shit to happen yet again. So I've been developing this small library recently. It is called LA, just LA. And LA stands for linear algebra. So it's a small library for doing a little bit of linear algebra in C. So it's a procedurally generated C library for linear algebra in 2D, 3D computer graphics. So basically, it's not the whole and comprehensive library for linear algebra. It's enough linear algebra to do computer graphics. So essentially, it's something similar to GLM, right? So how all of the C++ people, when they do OpenGL, they always use this kind of library. So it's basically that, but for pure C, and it's not following GLM conventions or anything like that. It's just like my own thing because I want to. So I'm going to put the links to these things in descriptions, of course. So a linear algebra source code, right, so this is something like this, and GLM source code if you're also interested in looking into that library as well. So what's up with that library, with the linear algebra library? So it says it's procedurally generated, and it is true, because it's actually really repetitive. In fact, it is in fact very repetitive. So let's take a look at this library. So here we have a bunch of vector definitions, right? And here are different operations for these vectors of different types, of different sizes. So you see, it is very, very repetitive. But one of the goals of the project, as README states, consistent naming scheme of the functions, types, and macros. So even though it is repetitive, there's a lot of things in here, you don't really have to remember any of the names of any of the functions because they have a consistent naming. Right, that's kind of the point. So essentially, the naming is as follows. If you want to create a vector, and our library right now supports only vectors, we're going to have matrices in the future. So you put V, so this is the vector, then you put a size as the vector. Let's say you want to have a three-dimensional vector, the 34-dimensional one, three-dimensional one, and then the type. So there are different types. There are integers, there are floats, there are doubles. I'm not really sure why I use doubles, but I do have them. So imagine that I want to have three-dimensional floating point vector. So the types in this library start from a capital letter, so that's the type of this vector, and then I will say that it's a position in 3D space. And if I want to construct this kind of thing, right, I'll just put the coordinates in here. So this is going to be a 1, this is going to be a 2, and this is going to be 3. There you go. I don't have to remember any of these function names, right? And then I want to add I will have some sort of a velocity of this object, right? And it's also going to be something like something random, 69 for 20, right, 23, and so on and so forth, right? And imagine that I want to basically update the position according to the velocity for a single frame for FPS of 60, right? Something like that. So what would I do in that particular case? Well, I would do vector3 sum, right? I'll add position and velocity, but since I'm doing that for a single frame in 60 FPS, I need to basically scale velocity accordingly. So what I need to do, I need to multiply this thing by delta time. But here's the problem. So delta time is probably going to be some sort of a scalar, right? Some sort of a scalar. And what's interesting about this library is that it has only vector operations. It doesn't have scalar operations, right? So if you take a look at this specific function, vector3 mul, right, so yeah, there's only vector ones. There's not a single scalar operation. Right, and the reason why it is like that is because you're supposed to construct a vector out of scalar. So essentially, there is a second kind of the vector constructor called scalar constructor. So what it does, basically, it takes a single scalar and turns it into a vector. So now a multiply is basically component-wise multiplication. So this is effectively taking a scalar dt and multiplying it by velocity. So the reason why I did it this way is because it reduces the amount of duplicated functions, right? For example, what if I want to do that the other way around, right? So I can do that, but you just basically extend the scalar to a vector, and you have like commutativity for free, essentially. So that's basically it. So, and every time you want to construct a scalar vector, it's basically V3 type, and the type again, right? And now you can construct a vector out of this thing. You want a 4-dimensional vector? Here you go. Here's a 4-dimensional one. 2-dimensional? Okay. So you want doubles? You do that. Okay. You see, I don't have to remember any of these names. The naming is consistent, even though it's repetitive. It is consistent, and it follows particular rules that are not that difficult to memorize. So, and it's kind of similar to OpenGL, I suppose, right? So you don't remember such things as GL uniform, uniform like 2i or 2f or something like that. It's just like they follow a consistent naming scheme, and yeah, so it's pretty easy to remember. So that's basically what we have in here. Another interesting goal of this project, right? So one goal is consistent naming, and another one is a human readable source code despite being procedurally generated. Right, so if we take a look at some of these functions, for example, right, I'm interested how the scalar constructor works for this thing, right? So for the 2-dimensional float vector, I'll just find the implementation, and this is how it works. It just calls to a regular constructor that just puts x and y into the vector and just returns it. So we also have our own lerp, and lerp has a pretty straightforward implementations. All of the functions have pretty straightforward implementations, right? So this is another sort of goal of the project. Despite this thing being procedurally generated, it is still human readable, and it's still explorable, right? So we don't obscure the naming of the functions behind macros or any other things. You get just a header library, right? You get just a header library, and you have everything you need to know, right? So you want to look up how a particular function works. There you go. It's pretty simple. It's very readable. That's how it works, right? Procedurally generated, but despite that, it's still human readable. You can explore that. Probably doesn't even need documentation, but I still want to document the naming scheme at some point. All right, so I think so far I met the first 2 goals of this project quite well. For more information on how, like, on more details of why and how I'm doing this kind of thing, I would recommend you to watch the first episode of this library development. So we already did 2 episodes, I think, and there is a playlist on Tsoding daily channel, so I'm going to redirect you there. So let me take a look. If I take a look at the playlists, where is the playlist? Okay, so linear algebra library generator. So here's the playlist, here's the first episode, and if you're interested in this kind of thing, go watch from the beginning. So linear LA development playlist. There we go. So it's going to be in the description, right? Just for you. Just for you. Okay, so, and here is the third goal. And the third goal is a little bit difficult to achieve, right? Minimal amount of dependencies, right? So you need to decide what is the acceptable minimum amount of dependencies. Well, our library is pretty small already, right? It is pretty small already, but it depends on math.h, which is reasonable dependency, I guess, if you're doing mathematics and stuff like that. Though I think we could replace some of the functions in here, like fmin and like fmax, because I mean you can just implement this kind of stuff yourself. So floor and seal, probably we could do that, but I mean it will just depend on the platform, so it would be nice to have like intrinsics for like compiler intrinsic for these kind of things. I don't know, so we still depend on mathematical library. But on top of that, there is a lot of functions in here. You see, there is a lot of them. I don't even know how many functions we have in here. So maybe within the generator, we could implement some sort of a counter, and when you generate a library, it will also print you statistics, like how many functions were generated, how many macros were generated, and so on and so forth. So that will be rather interesting. But maybe the next time, maybe I can even put a to-do for that. So to do print stats on how many things were generated. Oh, and another thing. So the end user of this library is not supposed to even know, or rather care. The end user probably will know, but they're not supposed to even care that this library is code generated. Right. So the end product, the end code that is shipped to the user is this header only library. The generator is not a part of a thing that is shipped for end user. The generator is a part of the development of this library, right? So, and I think it's quite important. Essentially, why it is important is because if you're end user of this library, you're not supposed to mess with the generator. You don't need the generator. You don't need anything, right? So you take already generated header and you just use it in your project. If you miss something in the library, maybe then you want to care about the generator. Maybe then you want to extend the generator and generate more types, more functions, more operations, and so on and so forth. But you're not supposed to do that every time on each build. So you just generate it once, right, and just use it in your project. So yeah, essentially the generator is called lag, right, for linear algebra generator. So because it generates LA. So it's part of the development tool, right? So the end thing, the end product is la.h. Right. And in the end product, as I already said, we have a lot of functions. Right. And by the way, we have a pretty extensive testing of this thing. So essentially, we build the generator, right? So the first thing we do, we build the generator. Maybe I'm gonna actually do git clean of dx just in case. Right. There we go. So this is a clean folder. So we build the generator, right? So here's the generator, and the generator, if you run it, it prints la.h into the standard output. That's how easy it is to use the generator. It doesn't have any parameters yet. It just like prints the library into the standard output. And this is the whole library, by the way. That's the whole library. So, and if you take a look at how many lines it generates like almost 2,000 lines of code of C, and it generates it within like 10 milliseconds. So it's pretty fast, it's pretty simple, nothing special in here. Nothing special in here. So the next step we do, we generate the .h library, right? So la.h, as you can see, we just redirect the standard output and to the file, and here is the end product that you're supposed to use. You're supposed to use this library, right? After that, we're testing if this header library compiles with different compilers. So first thing we test whether it compiles with a C99 compiler, right? So we force the standard to be C99. And the way we compile it, we basically enable all of the implementations, effectively making this header file a C file. Right, so this is the thing about STB style header only libraries. You can read about them more on Nothing's STB. It's a very interesting concept. If you never heard about it, it's just like single file header only libraries. So I really recommend to check it out. So I'm gonna put that in the description as well. So STB style header only libraries repo, right? So I'm gonna put it in here, right? So basically we define the implementation macro, effectively turning the header file into a C file, right? And then we compile it as an object file, basically checking if it's the entire thing that we generated compiled. Right, the whole thing. We just compile the whole thing and see if we didn't produce any garbage. So, and that produces la.c.o, and I put C in here because I wanted to indicate that we compiled it with a C compiler. Right, and the second thing we do, we try to compile it with a C++ compiler. Despite popular belief, C++ and C are completely different languages. One is not a superset of another. There is some things that, well, the part of the semantics of the language may differ significantly to the point that you may have a C code that doesn't compile with a C++ compiler. Yes, there's a lot of situations like that actually. But to make the library applicable in a wider range of the situations, I want my code to be still compilable with a C++ compiler. Granted, it's not that difficult to maintain actually. So you just avoid the places where the semantic between C and C++ is unclear, and you're done. You also support C++, and everyone is happy. So more people are happy, right? So more people can adapt your library. So, and that's essentially the whole process. So I update my generator, I do something within the generator, and then I just basically rebuild everything, right? So I just do make -b, and this entire thing rebuilds the generator, generates a new library, and builds the library with a C and a C++ compiler. And yeah, so this is how I check that I didn't produce any garbage. Pretty straightforward. So, and let's take a look at these O files, right? So the O files that get generated weigh 41 and 42 kilobytes respectively for C and C++. C is a little bit smaller, you see, it's a little bit more lean language, so you can shave off 1 kilobyte of data by just using C. To be fair, 42 kilobytes is not that much in 2021, but not that much compared to what? What if I have a small application that uses a couple of functions from this library? Just a couple of functions, and those functions could be like vector 2f sum that just sums up two numbers. And now I have to depend on 41 kilobytes of crap just to sum up two numbers, something that computers can do even without an operating system. You see what I'm talking about? I think it's bullshit, right? Even though, okay, 41 kilobytes, it's not that much, but I mean, if you compare things in a context, right? What if you do embedded and you find this library useful and you want to use it in embedded, and then you see these 41 kilobytes of crap and that you just like, well, I want to use that, and you can't adapt this library anymore, right? So again, I want this library to be applicable in wider range of situations, right? So especially if doing so doesn't cost me anything. And today I actually wanted to explore what we can do about this specific problem. Can we somehow get rid of the 41 kilobytes of crap if you don't use all of that crap? And you probably won't use all of that crap, let's be honest. Especially like there are such functions like I don't know, sign f, right? So if you never call this function, you never use sign f, and what if you never use anything that requires the math library? The question is, why the hell do you depend on math library then? You see what I'm talking about, right? So if you only use the things that don't require a math library, why the hell do you need a math library, right? So it's just like doesn't meet the last goal that I have in here, right? So minimal amount of dependency. I think it's not done yet. This last goal is not done. I think there is still some things we can do about the last goal. The first two goals, I'm actually like relatively happy with them, but the last one just doesn't fly. I think it doesn't fly. So let's go ahead and maybe implement a simple application that uses this library just to see what we can do about all of that. So what we're going to call this application. So maybe we're going to have just a point in, again, 3D space, and it moves to another point with a particular velocity, and we're going to just print and log its position over time. So, and that's a pretty small use case for the library, and it definitely doesn't use 99.99999% of the library. So it will be good to see how we can improve this situation. Okay, so we're going to call it foo, right? So let's include the standard IO library. And also let's include LA. Again, by default, these kind of libraries act like headers. So you're just including header, you're not including implementations. To turn this header into a C file as well, you need to define LA implementation. So the reason why you have to do that is because that gives you control over where your implementations go. If you have several translation units, you can put all of the implementations into one translation unit, and in a different translation unit, you can include LA as a header and reuse implementations from a different translation unit. You see, so that thing basically gives you more control, right? So a single file, basically both C and H file, right? And you just decide at which point how it acts. Like in here, I want it to act like a C file. So, and that's why I put implementation in here. Okay, so let's define an entry point and let's define initial position. So we're probably going to be moving in 3D space, right? Let's actually move in 3D space. Why not? So, and this entire thing is going to be oh, and by the way, since the library is so small, you can notice that v3f is just a struct. Maybe you can use like an initializer in here like this and just say initial position is 69, 420, 23, and there we go. So, and I think that will just work. I don't know what Emacs just did. Okay, let's try to compile this entire thing. So it's going to be foo C, and yeah, there we go. So I didn't even use anything from this library, and it already screams at me that it doesn't see any math library stuff. So I'm kind of already like, I didn't write anything, but I'm already forced to link with math, which is complete fucking bullshit, right? So it just doesn't make any sense. And the executable is 47 kilobytes, which is kind of close to these object files, right? It's kind of close to these object files. So I suppose something like without this library, right, let's actually take a look. So if I completely remove this bullshit and recompile the entire thing, right? So 47 kilobytes, it's 17 kilobytes, right? Like you shave off so much memory just by not using this library. And to be fair, this library doesn't do much, right? It's just like calls to other functions and just does arithmetic operations. Like you technically don't need this library. The question is, why am I developing it then? Well, it gives you a pretty useful convention, I suppose, to work with these kind of things. And I primarily do that for myself. So anyway. Okay, so we're going to have a particular velocity, right? So how we're going to be moving? We're going to move in probably, you know, similar direction. So let's just shuffle these things around. So, and this is going to be just a random direction in which we're moving. I actually want to shuffle those things a little bit more. There we go. So, and we need to have a delta time, right? So basically the time between the frames, the amount of time between the frames, yeah, essentially. So since we're going to have 60 FPS, I'm going to just take 1 second and divide it by 60, and delta time will be in seconds, right? It's going to be floating point in seconds. So let's actually simulate 10 frames, right? So let's basically simulate 10 frames. And in one frame, we're going to be printing the current position, right? So position is going to be equal to that. We're going to use the formatting macro, like this, and v3f arg. There we go. So I think, I don't know, I explained how these formatting macros work multiple times on my streams, but I can explain it one more time. Why not? So they come from the header thing itself. If we find 3f fmt, right? So essentially v3 fmt, the fmt macro, will be replaced with this. Right, so essentially it adds 3 formatting arguments to your string literal, right? And v3 arg takes your vector, right, and basically unpacks, or as JavaScript developers like to call, spreads. It spreads your vector into 3 arguments, right? Something like this, and this thing will basically become position. So in that way, it will print it, you know, as the vector. So basically, it's a way to add printing for custom types. Like, it's not the best way of doing that because it's relies on the macros and they produce horrible error messages. But it actually makes the complex printfs a little bit more manageable, right? So because you want to print one thing, so you want to have one format argument and one argument in the argument list. But since the vector is 3 arguments, now you're forced to actually juggle between like 3 elements, which you don't really have to, right? So it doesn't make much sense. So that's basically what it is. And I generated these macros for all of the types. So essentially now we need to simulate a single step. So what we need to do, we need to do v3f sum. We take the position and we add the velocity, but we need to scale the velocity by the dt. So, and the dt is going to be like something like this. All right, so that's basically what we're doing. This entire thing will produce a new position and we're going to reassign the new position. So that's basically it. So, and we simulating 10 frames. So if I try to compile the entire thing, it compiles, and if I try to run it, there we go. Here we have a simulation. So a point moves from this specific position in 3D space, and this is its position within like 10 frames and stuff like that. It's pretty straightforward. So, and if we take a look at this entire thing, it's still 47 kilobytes, but we're only using, how many functions do we even use in this particular case? I think we're using like 1, 2, 3, yeah, we're literally using 3 functions and 2 macros for it. We don't even use constructors in here because you don't have to use constructors if you want to just construct the structs, because they're, yeah, they're pretty straightforward. So it doesn't make any sense. It doesn't make any sense. So let's actually try to do some things with that. What if we enable optimizations, right? So what if I crank up optimizations as high as possible using O3, right? So there you go, I'm using O3. Will that help with the size? It helped a little bit. It went from 47 to 43, but it's still no near to 17 kilobytes, which I would expect if I just use a couple of small functions. So as far as I know, there's another optimization which is called OS, if I remember correctly. It's a size optimization, right? Is that a size? Yeah, I think it's a size because size went down even further, 32, 39 kilobytes. But I would expect even bigger. Like I would expect magnitudes of improvement, right? So like I would expect at that point of optimization, I would expect this thing to basically inline everything and remove everything that is not used. But it's not doing that. It's doing some sort of optimizations, right? But it's just not removing anything. And we can even check if it's actually removing anything. Right, so there is, in fact, a pretty cool command called nm, right? So it lists symbols from the object files. So essentially, each function definition, right, within a program usually produces some sort of a symbol, right? So this function will probably have a symbol when compiled to object file or executable. Executables, elf executables are also object files, as far as I know, right? Aren't they? Maybe they're not, I don't know. So, but nm works on executables anyway, so it doesn't really matter if they are not. So, and each of these things produces the symbol. So, and we can easily see if we still have those functions in there. For instance, here are the object files of the library itself that we used for testing. So let's actually call nm on one of them, right? So I'm going to call it like this. And there you go. We have all of these symbols, of these functions are in here, right? We can even probably do something like obj dump, right? Obj dump, it displays information from object files, which is kind of interesting because nm technically also displays an information from object files, but very specific one. Obj dump displays different information from object files. And there is also another utility called readelf, which displays information from elf files, but object files are elf files. So that's kind of sus. Wait a second. So we have that, and we also have that. It lists symbols from the object files, displays information from object files, displays information from elf files, but object files are usually elf files. So Unix philosophy, by the way. Anyway, so the reason why I want to use object dump is because of its -d flag, right? And it can disassemble things, right? So we can just go ahead and even see like how the assembly of this thing look like. So I'm going to do co and let's go. So here are all of the functions and here are their assemblies. Right, so here is the v2f constructor, and this is how it compiled down to. So, and you can see we use all of these functions in here, pretty straightforward. So again, I compiled foo with these sort of optimizations, right? And if I take a look at the symbols in there, the symbols are still there, right? So we cranked up optimizations as much as possible, different kinds of optimizations, size optimizations, like performance optimizations, but the symbols are still there, right? So it didn't really remove anything. There's also a lot of symbols from the C runtime, as you can see, so it's a C library. So it still depends on sine and cosine. I have fly in here. So it depends on all of these things which are not needed still. So, and if we take a look at the, assembly of this entire thing, it's going to be foo, and that's a lot of shit, actually. Holy fuck. So, where's the main? Okay, here's the main. And interestingly, well, here's an interesting thing. Within the main, so here is the main function, right? I think this is a clue. I think this is a pretty good clue. So that's the main. And in the main, in the original source code, we call to all of these library functions, right? Do we have a single colon here? Oh yeah, we do. We call to printf, as you can see. We only call to printf, right? Do we call to anything else? No, we actually don't call to anything else, right? So even though in the original source code we call to all of these functions, there is not a single call to those functions in the final assembly. There's just none. They were all inlined. So it did in fact inline them. It did in fact inline them as far as I can tell, but they're still in the object file. So that's kind of sus, isn't it? That's kind of sus. So if I take a look at the temporary output, maybe a sync output, yeah, there we go. So they're still there. So it inlined them, but it never calls them. It's just like they're there as like a dead garbage. And the reason is because they all are declared as external symbols. Yes, that's the actual problem here. That's the actual problem. So look, the default declaration of the functions is assumed to be an external symbol, meaning that it has to be visible outside of the translation unit, outside of the object files. Right, so the object files can be linked together, and so that means it allows one object files to use functions from another one. By just declaring a function, it's by default public. So compiler have no choice but include all of the functions in the final object file, because we kind of explicitly, well, implicitly told the compiler that somebody may use these functions from a different place. So it did as much as it could to optimize the main code that is doing the job. It inlined everything, but it cannot remove anything because, well, there's no command to actually not include anything, because everything has to be public, right? And since everything has to be public, it has to be included, right? The question is, does it really have to be public, right? So here's the thing. This is a single header header only library, right? So it's usually included, the implementations are usually included as they are, right? So they're usually baked into the executable. So maybe they don't really have to be visible. So maybe one of the things we can do, we can say, okay, so all of the functions in here are going to be declared as static, right? So, and let's just go ahead and see if it will help with the size of the program. So this is going to be vec, I forgot how you call this, generate function, yeah, there we go, generate a function signature. So every time we generate a function signature, we call to this function. So that means if I add a static in here, it will add static in front of each and individual function call. Let's actually see if it's going to happen. So I'm going to do make, and I'm going to regenerate .h. There we go. We regenerated .h, and let's take a look at .h. Here it is, and we have a static in front of each individual function in here. So you see. So that's, by the way, why I'm using code generation, right? If I want to add static to all of these functions, I don't freaking want to do that manually, right? So I want to have a code generator, so that does that for me. Anyway, so we can try to recompile the entire thing and see if it's gonna improve anything. Oh, all right, this one is interesting. Defined but not used. Oh, I see. I do remember, because we compile these things with all of the warnings enabled. And GCC, by default, as far as I know, complains about unused static functions. Since static functions are not visible outside of the translation unit and you don't use it, so nobody else can use it. You see? So since it's not visible outside, nobody can use it outside, and you inside also don't use them. So nobody uses them. Why do you have this function? Do you have a bug? Do you have a dead code? Remove that. So yeah, actually remove that. So, but it's just a warning. It doesn't really, you know, stop the compilation. It still generated something, right? And so the object files that we got generated, they are still the same size. Nothing was removed so far. So let's try to recompile the full program. Let's try to recompile the full program and see if anything is going to be improved. Let's actually try to compile it without any optimizations. Let's see how the compiler does all of that without optimizations. So the executable is still big, 47 kilobyte, and let's crank up the optimizations. And it went down to 17K. Not bad. And as far as I know, 17K is basically the same as not using this library at all, right? So if I just try to do this kind of thing, and yeah, we're not using anything, it's 17K. Right, it is 17K. So that means if we declare all of these functions as static and crank up all of the optimizations, the compiler will have enough information to actually inline and optimize everything. Right, so as you can see, yeah, so I'm going to do something like O3. There we go. And we can take a look at what kind of symbols do we have in this executable. And as you can see, we don't have a single symbol from this library. Not a single one, because they all are internal, and since they're internal, nobody needs them outside, so you can inline them and remove them. And that's what the optimizer actually did. That's what the optimizer did. So, and now I can take a look at the object dump and disassemble foo. So what do we have in here? And look at the assembly of this entire thing. The assembly of this entire thing is 200 lines of code, compared to the assembly of like when before we had this kind of optimization. And the main, let's take a look at the main. Main should be, main should be pretty much the same because it was inlining them anyway, right? Yeah, main looked pretty much the same. But now we don't have any of this extra crap and stuff like that. But we have a problem, right? So it's rather interesting actually. So what if I don't have any of these optimizations? It's funny that it doesn't complain that we have unused. Yeah. So because we never actually enabled warnings, right? If we enable all of the warnings, which the user will probably do, if they care about the quality of their software, they will probably enable as many warnings as possible. Now they will have annoying thingy saying that, yeah, you have unused function and, right. So if you don't include LM, it will still complain about not being able to link with LM as long as you don't enable all of the optimizations, right? So there's still a lot of problems in here, just marking it as static and stuff like that. So as far as I know, to get rid of these kind of warnings in GCC specifically, maybe the same is in Clang, you actually have to declare your static function as inlineable, right? So let's give it a try. Let's include it as inlineable. And inline in C, it's really controversial feature, right? So it is a rather controversial one because a lot of people will tell you that in C, inline is pretty much useless, because it acts like a hint for the compiler that a particular function is inlineable, but it's up to the compiler to decide whether you want to inline that thing, whether they want to inline that thing or not. And since modern compilers are so smart and super optimizing, they know better than you anyway whether you want to inline this thing or not. So, and because of that, like the conversation about inline in C is rather strange. But on top of that, on top of being just a hint, as far as I know, inline enforces a little bit of a semantic to help the compiler to inline things better, right? For instance, I think if your inline function is visible outside of the translation unit, meaning that it's an external function, it may not do certain things that will prevent inlining that function from the external translation unit, I think, like trying to modify like static stuff or whatever, right? So it just forbids you doing these kind of things. And as far as I know, in GCC there is a trick for static functions warnings. you just basically declare them as static inline, right? And if you have a static function that is not visible outside of the translation unit, and within the translation unit you don't use it, but it's inlineable, the GCC won't throw any warning. Right, the GCC won't throw any warning. So we can put that in line just to suppress the GCC's warning. And I personally would use this library primarily with GCC and Clang, and I personally don't want to see this kind of warning. So I will just throw in line specifically for that case in here. Right, so let's see if it's going to improve anything. So now if I try to compile the entire thing, will we have any warnings? Okay, so we don't see any warnings. And you may notice a very interesting thing. The sizes of the object files went down to almost 1 kilobyte. But here's the strange thing. Here's the strange thing. We don't compile any of the headers or any of these things with optimizations enabled. That is really sus, isn't it? So if I basically remove inline, no optimizations, we don't tell the compiler to do any optimizations, like use your default optimizing thing. And with the default optimizing thing, it basically includes all of the static definitions, right? And with the static inline, without any optimizations, it removes all of them. No optimizations, and we already have an ability to get rid of the dead code. I wonder if it will work with O0. So we're gonna explicitly say, don't like apply anything, don't optimize anything at all, like just completely off. Yeah. So let's recompile one more time. The size is still down. So GCC specifically removes dead inlineable functions, even with all of the optimizations turned off, which is rather interesting. So is inlineable function really that useless, and compiler really knows better than you? I don't know. So we disabled all of the optimizations, and we still got some pretty cool optimizations, just getting rid of the inlineable functions. And let's actually test that on foo, right? So let's take this on foo. So I'm going to compile the foo without any optimizations and without even LM. And it just compiles. I don't enable any optimizations, and I don't even link with LM, right? And it compiles, so it gets rid of all of the calls to math library, like cos f and so on and so forth. And now we literally have the zero cost abstractions, right? You know how C++ and Rust developers like to say, yeah, we literally have a zero cost abstraction. Essentially, we literally don't pay for what we don't use. Which brings us closer to the third goal, actually. It brings us closer to the third goal of minimal amount of dependencies. Yeah, now you just literally don't pay for what you use, at least in GCC. Because this is the behavior of GCC. As far as I know, it's also behavior of Clang, right? So if we try to use Clang, right? So what Clang will do? Yeah, Clang acts the same. I might as well even try to compile the entire thing with Clang. Oh yeah, that one is interesting. So Clang will still complain about unused function. I wonder why though. Is that because of all of the optimizations turned on? So with all of the optimizations turned on in Clang, it will complain about that stuff, and it will, yeah, Clang will complain a lot about this kind of thing. I wonder. But GCC at least won't. GCC at least won't complain about this kind of thing. Truly, truly sus. Also, I think I didn't check if GCC produces shit ton of crap. It actually doesn't produce shit ton of crap, so the object files are a little bit smaller. So I'm not even sure how it will act in TCC, for instance, or maybe in MSVC. So, but for GCC, which is the compiler that I'm probably going to be using the most, it's fine, I guess. So yeah, I think we're going to basically mark all of these functions as static inline, just yeah, static is needed to let the compiler know that you know, you can do whatever optimizations you want with this thing. You don't have to include it if it's not needed. And inline is just in case. Maybe it's going to be useful for some of the compilers, right? So yeah, and also it will enforce the semantics that will you know, help the compiler to do the optimizations. But here's an interesting thing that reduces the flexibility of the libraries. What if this is exactly what you want? Right. What if including shit ton of crap is precisely what you want, right? So maybe you're okay with that, right? So, and now you cannot include shit ton of crap. I think we need to make this thing sort of customizable. So the usual thing that people do with these kind of libraries, right? They define a macro, static inline, something like a def macro, and they prefix it with the name of the library. So we're going to call it ladef, linear algebra definition, right? And then we're going to define a special macro, right? We're going to define a special macro somewhere here in the header definition. So I'm going to put it here, fprintf stream define ladef static inline, right? So, and this one has to be a new line in here, right? So, and let's recompile the entire thing. And if I take a look at this thing, there we go. So all of the functions, function declaration have ladef in front of them. So, and the next step that you probably want to do is to actually wrap it into the following logic. You want to define this thing if it's not defined, right? If it is not defined, there we go. So something like and if, right? So basically, if the user defined their own ladef, we don't define our own. But if the user didn't define, we use the default one, and default one just marks everything as static inline, right? By default, it's going to try to help the compiler to optimize as much crap as possible. So that's basically going to be the idea. All right, so let's give it a try. I'm going to just do up, and there we go. So maybe we're going to want to try GCC, and of course I already did some sort of a mistake, so I should have actually put a comment in here, right? And everything seems to be working. Okay, so if I try to compile now foo, right? So here's the foo. I compiled foo. It's fine. And now let's say I want shit ton of crap. Well, I can define ladef like this and make it empty, right? Then I can go back and I recompile my entire program. And now, as you can see, it complains that it cannot link with the math library, and I can just link it with the math library, and there you go. I have shit ton of crap in here. So I asked for shit ton of crap, I got shit ton of crap. So if I'm not happy with that, I'm going to be just doing that. I'm going to remove this entire thing, and the entire thing is going to be pretty good. So basically, we give the user more control over the things that it can do. So this is not ideal solution, but at least it brings us closer to the third goal, right? It brings us closer to the third goal, and on some compilers you can at least now do something to get rid of the unused functions. So maybe we can push that idea even further, right? At some point in the future, right? At some point in the future. And for instance, if you don't use like a vector2, maybe we're gonna have something like if not def LA disable v2f, right? So, and then it's going to be something like this. And if you don't use something, you can just define this macro, and it's not going to be even in the final source code. So that way you can like precisely control what goes into your source code and what doesn't go into your source code. And since we're using like a code generation, it will be pretty easy to add this like sort of macros in here. But maybe we can make the thing that everything is disabled by default, and then you enable some things, right? So maybe at some point you're going to say, okay, I'm including that, and in here I want to do LA v2f, right? I need v2f and I need v3f, right? And so that includes everything related to these things, right? So, and that way you can control what you have and what you can and what you can't have. But maybe I'm going to do that a little bit later. I don't think it has that much of the priority right now. So yeah, that's basically everything. So it's kind of cool. Yeah, it's kind of cool that you still need inline, and it like greatly impacts the behavior of the compiler. And again, the behavior may be different in different compilers. So you have to constantly keep that in mind. You have to constantly keep that in mind as you design your library. So yeah, let's maybe do a committee, and maybe then even a pushy, right? So as usual, what do we have in here? So I introduced la dev, and let's remove foo. So make all the functions static inline by default, and I'm gonna push that right into the repo. So yeah, that's pretty much everything I wanted to talk in this specific video. So thanks everyone for watching. Check out all of the links in the description. Check out the like how we started the development of this library, right? So in the first episode we have a lot of discussions on why I started this kind of thing and so on and so forth. So maybe that's going to be interesting. So yeah, thanks everyone for watching. Love you.